Hello everyone, my name is Louis and today I will show you the first of the three MATLAB based programs from the XCT Toolchain which were made to handle high resolution X-ray MµCT imaging of tree rings and increment cores. Okay, so the first program is the CoreProcessor program, which you see here on the top left. This program was made to digitally extract the cores from the scans and convert them to absolute density. And I'll show you what I mean by this. So when we make scans of increment cores, we put them in this kind of holder, which is like a long plastic holder with all kinds of holes in it, with a bunch of holes in them. And the increment cores are in paper straws and they go inside these holes. And so when you have a scan, a CT scan of these samples, you will have a scan with many different samples in it. Okay, so the first challenge is getting this scan, going from this scan with many samples to individual cores, individual digital 3D cores. Okay, and for that we use the CoreProcessor. I will first show you what one of these CT scans can look like. So, for example, I have two here. This is one from the high resolution holder. So this is a 50 micrometer voxel size holder. And so if I zoom in here, this is a 3D image that you get out of our CT scans. So if I go through it, you can see we go slice by slice, we go through the holder and we see the density changes. Okay, and so all these things are increment cores with tree rings that we want to measure the density of. And these two are the reference holes. So this is a POM, a type of plastic, which is seen as as a pure wood density reference. And here we have air, which is a zero reference. And so we will use these two references to convert all of these to absolute density values. Okay. So this is the high resolution scan, with 16 samples. But we also have a medium and lower resolution holder, which looks like this. It can fit 48 samples, which you see, much more. If I go through it, again, the same. And here we have 3 reference pairs. So for each layer, there is 1 reference pair. Okay, so 1, 2, 1, 2. So first, to get started, you will need to download these programs and install MATLAB Runtime. And for that, you can go to our website, so dendroeconomics.ugent.be. Here you have all kinds of information on the scanning process and what we do and how to collaborate with us. And here under Downloads, you can find the 3 software packages, which are hosted on GitHub. Please always check for the latest versions because we do regular updates, and so the latest version will also always be here on this GitHub. You will also need to install MATLAB Runtime, which is a MATLAB compiler. At the moment we're on version 2024b, but this will change, and so always check on the website which version you need for the latest version of our software. Okay. On here there is also some manuals and test volumes which you can download and some more information. Okay, good. So let's open the program, the CoreProcessor. The first time that you open it, it will take a little bit of time because it needs to load the whole MATLAB, but once it has loaded, we have it here. So the first thing we need to do is prepare a core extraction, but I will first show you the Excel file that you should have filled in during the scanning process. So if we go here, I have 2 scans here, one that is 50 micrometers and one that is 30 micrometers. And for each scan, you will need to fill in an Excel template. And these Excel templates are also on the GitHub. And so when I open it, it is on my other screen. Yes, okay. When I open this Excel template, you will first see all types of metadata that you need to fill in. So for example, how many air references do you have in this scan? How many density references do you have? Well, POM plastic references do you have? And how many cores? Yeah. Also, what is the density of the reference, but this shouldn't change. And what is the resolution, well, the voxel size at which you scanned. So that's over here. But normally, if you use the same type of holders as us, then you don't need to change anything here. And otherwise, it's just a single change. And after that, it should always be the same. What's more important is here the core data. So these are the locations. So the locations within this sample holder. Within the sample holder, each hole has a number, which is laid out here. They all have a number. And so each number has a certain sample, and we tell it here which one it is. So in the first hole, we always put the POM, so the plastic, and it is indicated by here the type, it's a reference, and we call it POM. Then here we have the name of the first sample that we put in here, and then an air, which is also indicated like this. Okay. All the rest are cores, and we gave them names. You can give them any name you want. Good. This is just an example of one of a scan that I did recently. So these are the names. Good. Quickly, I will also show you what a 30 micrometer one would look like. So many more samples and multiple air and references. So here I have 3 airs and 3 POM references, and also 48 cores. So this has changed. And also, of course, the resolution is lower. Here we have a voxel size of 30 micrometers. So in the core data, that also looks a little bit different. So in the beginning, it's the same. So POM1 and air1. Okay, but then as you go through all the numbers and the other holes, in, for example, number 15, 13 and 15, we also have a reference. So 13 is POM2 and air2. And the way to tell this to the program is to, again, say here, this is a reference, this is an air, and the other ones are cores. And we put them in group number 2. So this group, all of these cores, are corrected, well, are transformed to absolute density using these 2 airs and refs. So within this same group. Then all of these cores, which are in group 2, are corrected using this reference and air. And that's useful because that way we can like group within a certain radial section. We can group all these cores and say, okay, everything in this row has to be corrected with these 2. And this can combat certain effects like beam hardening, which you often have in X-ray CT. Okay, so that's the way that works. And you also have a third group, just reference, air, and all the other ones are just core names. Okay. Good. So this you should have made during the scanning process, and when you're loading the holder and put them in the scanner. Now I will show you how to actually perform the extraction. So going from this full scan, which has been reconstructed, to individual cores. And we will do this first by clicking Prepare Core Extraction. And so it will ask you, select the folder with the reconstructed files. So when we go to my folder here, we have the sample scans here, and I will start with the 15 micrometer one. This. So I tell it it's here. Select folder. I will quickly show what this looks like. So in the 50 micrometer folder, there are just all TIFFs, which are numbered, ordered, so it knows what the order is. Okay. So then it asks select the Excel file with the metadata. So we go a bit up, and I think I put it here. So I say 50 micrometer. This one. Open. Then it asks me where should I put the MOT files. So the MOT files are the files that it stores, where it stores like the information that I will put in. So for example, here is this sample, here is this sample, the locations of the samples and the names of the samples, they will be stored in a MOT file. And you want to put them all in like a central location so you can later do like batch extractions, which can sometimes take a long time. So I will put them here in my main folder, like the sample scans, where I have all of my 2 scans in this case, but you can have many. So select folder, Okay, now it is loading 100 files from the scan, well, 100 slices from the scan, which are evenly spaced. And so the first thing that it asks me is select one times an air reference. So you can do this by clicking and dragging. In this program, we have these round things, and you can change them from size. And if you are happy with the selection you made, you can double click, but I won't do it yet because I need to explain some more. So when you select a reference, both the air and the POM later, you need to be sure that it's a location where there's only air. So never do it like this, or make it too big and that there's like little bits of plastic in it, whatever. Always stay away from the edges so that you're absolutely sure that through the whole length there's only air. So it looks like this. Okay. So the image, by the way, that you see here is the average of these 100 slices throughout the sample. So I am happy with this, and I say double click up. Okay, and now this air reference is fixed. Then it asks me select one times a normal ref, so the plastic ref, which is here. And again, I just take nicely the middle and only the location where there's a POM. And I stay away from the edges just to be sure. Okay, and nicely in the middle. Double click, okay. Then it has to calculate a little bit, okay. And then it shows me what it looks like. So what the gray values are of the POM throughout my core, throughout my scan, and of the air throughout my scan. And so here you can see if there are any problems. So for example, there's a big dip for some reason because you accidentally put a little bit of plastic in it, or like the air hole wasn't completely clean. But here it's nice and straight, so it looks perfect. Then it asks, do you want to use a linear trend through this? Because there's like a little bit of variation, of course, in this. Do you want to use smooth values or the raw values? I highly do not recommend to use the raw values. It's much better to use these two, and usually a linear trend is quite fine. So I use this. Then it asks me, how do you want to select your samples? And as we have like round samples here, I will use an ellipse. Okay, so now it asks me, select 16 times the sample, mind the order. So first, now I have to tell the program where my samples are, and I have to do it in the correct order, so I will start with sample number 1. And so if I go back to my Excel file, the locations, so these are the two references which we already indicated, and so in between the references, in between the POM and the air, we have the first sample that should be indicated because it's number 2. And after that we go to 4, 5, 6, 7, 8 and go all around. So I will do that now. So I will start with the first one and I indicate it like this. You can indicate it very nicely, like I did just now, but you can also do it like a bit faster and a bit ugly. It doesn't really matter, because in another step after this, which I will show you, we will crop it anyway. So you can do it like this. Okay, and I will go and I double click to say okay, and then it knows, okay, it's this one. And then you go to the next hub. Okay. Okay, now we're done. And the next step is to indicate how the fibers, what the fiber direction is. Okay, so be careful, the fiber direction isn't the same as the tree ring border direction. So for example, here you see a tree ring border, but if you look closely, like the fibers and the resin ducts, they go along here. So you have to indicate this on the central slice. You just click and drag and you give it a line. And it shows you along the whole core, it's like evenly spaced along the whole core, shows you what that looks like. It's not critical that this is super exact, and very often in like dried cores or for example tropical species, the fiber direction will change throughout the core. That's why later in RingIndicator, when we indicate the rings, we will indicate it in 3D anyway. So like this step being super exact doesn't really matter that much, but it's better to do it as good as possible. Also, the sample, the bark, so the lowest part of your sample, the most recent part of your sample will be here. And this is the most upper part of your sample. And often when you get closer to the center, get further away along the core, so over here, you will get near the pith and there will be a lot of turns and there will be a lot of defects. So I always suggest to put more weight on this part of the core than on this part to like choose your direction. But here I think I will do it like this. And if you're okay, you double click again. Okay. Then the next step is to crop. And so here you crop the volume as you wish. What I usually do is just crop some of the edges off so that you have like a lot of core. It's always the most important that your the center of this like imaginary cross is like nicely in the middle of your sample and that it always has sample. But like these edges here are like never used in density calculations because we will use the middle anyway. So I make it a little bit bigger so you have more room for seeing like unclear rings and for cross-dating purposes and stuff. So I would do it like this. And I double click. And now it goes through all of these cores. Up. This. Like this. And I will do them all. Okay, now we're done and we go back to the screen and it will have added this one here, so the mat file in the main folder, which indicates where all my indications were, and it will also have saved like the positions which I indicated and the reference curves. Okay. Now you could do the core extraction already, but it's more handy to do all of your scans in one go, like indicate all of your scans, and then put up the extraction during the night or whatever, because this takes a long time. So first I will also indicate my second scan, which is the 30 micron one. So again, I click Prepare Core Extraction. I go to my folder, sample scans, 30 micrometers. Okay, then it asks for the Excel, this one. Then it asks for where to put the MAT files. Again, I will put it in this main folder. Okay, so you see we have many more samples now, but first it asks to select 3 times air. And it's important to do this in the correct order. So start with group 1, which is the middle group here, then 2, then 3. So I will start over here, put this nicely in the middle, double click. Then the second one, double click. And again, it's important to stay away from these edges so that you're in a nice bit of air. Then 3 times the ref again. So start with group 1, put it there, there, and that's the last one. Now it will calculate the things again. And so you see for each group, there are different gray values for example, the POM and also the air, and that's why we have these different groups, so we can correct for beam hardening in this way. I'll again use a linear trend, and then again use ellipses. And I will indicate all of them like we did last time. Okay, I have now indicated all of them. And again, we now indicate the direction of the fibers. The last ones were softwood. This is hardwood, mostly tilia. So here the fiber direction is a little bit easier to see. Okay, we are now done. We have indicated both of our scans, but you can do many. And the mod files, which are needed for the actual extraction, are all in the same folder. It's important that you put all of these in the same folder, so then the extraction will automatically do all of them. Okay, to do an actual extraction, we click Core Extraction. Please note that this step will often take a very long time if you use large scans. For example, most of our scans are around 300 gigabytes in size. This does not mean that you need 300 plus gigabytes of RAM, but we suggest that you use at least 64 gigabytes for this step, but sometimes you can get away with less. So here I'm doing this on my laptop, so I have just two super small scans here, so they are only like 3 gigabytes, only a super small section of the scan. So instead of the full scan I have loaded here, I only did like a centimeter or something. Okay, so I do core extraction. And then I tell it where are the mod files to do the extraction. So they are here in this folder. I say select, and now it is doing it. So first it will extract the air and the reference files, the air and the references to make the curves. It shows me, but you don't have to do anything. This is fully automatic. You can just run this at night. You can click it away, and then it is extracting the cores. Here the cores are super small in size, so it's extracting all of them at the same time, so 1 to 16. But if you have like a large scan, this will not fit into your RAM, so then it will do, for example, like 2 at a time and just go through the scan multiple times until it has extracted all of them. This is almost done, and now it will be writing the cores. It writes the cores. Okay, it is now writing the last core. Okay, it's done with the first holder, and now it goes to the second holder. And here it is again, first extracting all the airs and the references. It is doing all 3 pairs in one go, because it's a small scan, but in larger scans this could be 1 by 1. Here we have the full curves again, which look very nice. And now it is extracting the cores. They are small, so it's extracting all of them at the same time, but it could be in multiple steps. Okay, it's now done. It has extracted all the scans that we indicated. Let's have a look. So you can click this away, and this is again open if you want to do anything else. But so first, let's go to the 15 micrometer scan, which looks like this. So we have the original scan files. And here it made 2 folders, so the extracted and tangentially corrected cores, and also some single slices. So let's have a look at the single slices. The single slices are just a JPEG of the middle slice, which you can use to quickly evaluate what your scans look like and if everything is fine. So for example here, note these are super short cores. It's only like a few centimeters, like a centimeter or something. Because these are small, this was a small scan, I will show you later a normal one, a big one. So, but you can use these to look at and evaluate. But the actual extracted files are over here. And they are called the way that we told it in the Excel file, and it's per core 3 files. So 1, 2, 3. So first a core which has the actual name. So here DMH63 2015, and then the same name but a radial file and a transverse file. So a transversal file. And so the main file is actually this one, and you will also see if I go to details that this is the big one, so it's 29 kilobytes, and these are smaller ones. This is a TIFF file from the middle in the transversal radial section, and the other one is the middle of the transversal section. These two files are used by the next program, the RingIndicator, to just quickly load and display what your file looks like, what your core looks like in the two main axes. Okay, this is to avoid having to load the full large volume every time you open a core. Here it's quite small. It's 29 kilobytes, 29,000 kilobytes, so 29 megabytes. But when you have like full scans, large scans at high resolutions, it's very common that you have cores which are larger than 5 or 6 gigabytes, and having to wait for this to load all of the time, and needing computers to be able to load this is annoying. So that's why we have these two. Don't worry if you lose these or you delete one of these radial or transversal files. When you open a core in RingIndicator, it will automatically make a new one if you lose it. So let's quickly have a look in Fiji, what this looks like. So this is one that we extracted. Okay. I will quickly make up. And so this is the core that we extracted in 3D. And when you open the radial plane, it looks like this. So it's like the middle here, but sliced in the other direction. And it's only one file, it's not 3D. And the same for the transverse. Here you go. So this one looks a little bit noisy, much more noisy than these. I will make them bigger. Okay, so this one looks a lot better than this, because this is actually the 10 middle slices averaged out. Because we have super high resolution, so super thin slices, which mean that every slice only has a limited amount of information. But we will always just average out in the Z direction to make the CT scans more clear. Okay, so it will look like this when we open it in a program. I will now quickly show what a real, a big one looks like. So I go, for example, here to my sample cores. And if I open this up, this will take a bit longer to load because it's 3 gigabytes. Okay, it's there. Up, auto. So here you can see the core that we extracted in 3D. And so this looks a little bit noisy because, again, it's only single slices. So these are inherently more noisy. But if we go to the transverse TIFF, we load this, we can see a beautiful core with nice density fluctuation. So here we have a low density latewood, and here we have a more high density latewood. And so this is a normal type of core which you will get out of our toolchain. And this is 15 micrometer resolution. Okay. So next, I will show you what else the program can do. So these two are the main ones. So prepare the core extraction and do the actual extraction. But if you, for example, have a file and the tangent correction was not very well and you want to change it, you can always redo it here. So click on this and it will open all the scans within a certain folder, and you can do redo the tangent correction. You can also flip cores or glue cores together. I will show that here quickly. So if I go to my sample scans, the 50 micrometer one. So for example, say the first one and the second one I didn't put in the holder correctly, because when we scan we always put the bark down in the holder, but sometimes there can be a mistake and you put it in the reverse, and so we need to be able to flip these cores. Then you copy these two, make a new folder, so here, flip, put them here. So these are the cores that I want to flip. Please note, don't put the transverse and radial files, like the small extra files, in here, because these will not be flipped. Just delete those, remove them, and then the first time that you open these cores in RingIndicator, so the next program, these transverse and radial files will automatically be created. So always delete them whenever you do something. So for example, flipping or gluing or cutting an ImgJ. So let's flip these. Here. So flip, I want to flip everything inside of here. Select folder, it loads them, saves them, loads them, saves them. And now inside flip, we have two flipped cores. Okay. What else can you do? You can glue two cores together. So our holders, our sample holders, the high resolution one is 35 centimeters long, which is usually more than enough for most samples, but sometimes you have samples which are longer than 35 centimeters. And then it is useful to just put them in different paper straws, scan them as separate scan them as separate samples, and then glue them digitally together afterwards. That way, in RingIndicator, you can just have one file for one core, which was too long, but we can digitally glue them together. So, for example, let's say these two that we flipped, we want to glue them together. We say glue cores together. Select the one on the left. And it's important, the bark side is always on the right in our program. So the bark side is on the right, so the left should be the older bit. Let's go. So sample scans, up. Let's take these two as an example. So let's say that this is the older part and this is the bark side part. So up, open. Okay, then it asks for the right one, this one, open. And then we can give it a new name. For example, if it was A and B, then we can remove the A and B and just make it the full core. Glue. And now it is in here. So the glued file, I will maybe quickly show it in ImgJ. So now these are not correct because we flipped them, but and they don't really belong together, but now they are glued. Also here in the middle we have a little black space so that it is clear that this is a spot where you glued digitally, and so there is no confusion here. A small remark on how the files work. So when I zoom in, the gray values stand for the density, and so when I go here, you can see, when you look here in ImgJ, you can see, for example, this pixel has a density of 731 kilograms per cubic meter. In the early wood it will be lower, so 200, and for example here in resin duct it's even lower. It should approach, well, on average it will probably approach around 0 because it's air. And the areas around, so the areas around the crop which are not needed, these are minus 9,999, which is our not available number, so not a number value. These pixels will, when you load into a RingIndicator, will be ignored and will never be taken into account in density calculation. So you can always use this value as a kind of an empty space in your scans. Okay. What else? These files were all made in such a way that we can also do more complex editing in ImageJ and save them, and that RingIndicator will still understand. So, for example, I again load this file. In ImageJ, yes. So in ImageJ you can, for example, reslice, or make straight, or crop, or do whatever. For example, like this. Up. I'm gonna make 500 slices here. Okay. Fantastic. So I resliced it, and for example, I want to crop it also. So like this, and I go to Image, Crop. And this is now my new image, which is for some reason better. It's a fictive case here, but just to show, this is now my new image. I don't want this anymore, and I want to save it. And you can just save as TIFF. The glued, the better one, save. Yeah, I want to replace it. And now this one, the new file here, can also be read by RingIndicator, have all of the information about resolution and holder type in it, and everything will just work. And we built it that way that you can also edit your scans in Fiji, and the whole toolchain will understand. Okay. Is there anything else? So on the About page, there is always a link to our manual, which are on the site. Also, how to cite when you use our toolchain and our software. So these are the papers you have to cite, and the Zenodo for the software. You can also find the latest version always here on GitHub, and we use this type of license, and all of the information is in here. Okay, when you're done, you can exit, and then you're done.